Now, as the last item of this lecture, we will discuss the electron inside an atom. Okay, now the story goes like this. In late 19th centuries, scientists have observed the spectra, the light spectra coming out from hot gas of atoms, and they have observed something like this. So in this example, you see that the spectra does not come out continuously, but they appear as discrete lines as a function of wavelengths, which are represented by different colors. So people have observed this, and experimentally they had a very good idea, and certainly they tried to understand why. But it was very difficult, and a scientist whose name was Balmer actually tried to guess. He was a mathematician, so he didn't know much about physics, but by simply carefully watching the results, he came up with a formula which can explain these wavelengths. For example, this equation, which is called the Balmer equation, if you insert n equals 3 here, then you will get this line. And if you insert n equals 4, you will get this line. If you insert n equals 5 here and here. And as you can see, this actually the left-hand side is inverse of the wavelength. So therefore, when you insert higher number of n, then you will get smaller number of wavelengths. Okay, this is simply something that Balmer guessed. And of course, he didn't know why. Okay. And it was finally Niels Bohr in early 20th century who finally came up with a theoretical idea to explain this Balmer equation. Okay, so in doing so, he made two very bold assumptions or strange assumptions in his time. So first thing was that he assumed that electrons orbit around the nucleus in a circular orbit, just like the Earth is orbiting around the sun or the moon is orbiting around the Earth, right? Okay, so that was his first assumption. And that was actually okay because the electron is negatively charged and nucleus is positively charged. So therefore, there will be some Coulomb force acting. And he made another very strange assumption, which is that the magnitude of angular momentum of electrons is quantized like this. This L here is the angular momentum, and he assumed that this angular momentum must be integer times the Planck constant divided by 2 pi. So why did he assume this? Of course, in the beginning, he did not know. He simply thought that in order to get Balmer equation, the total energy and also the angular momentum must be quantized. So he tried to get the right solution by assuming this. So based on these two assumptions, he tried to calculate, okay, what is the first to calculate? Of course, the force equation. You know, the left side is simply the Coulomb force between the electron and then the proton, which is a nucleus of hydrogen atom. So the charge of electron is minus E, and charge of the nucleus is plus E. So therefore, you have a E square here. And then on the right side is, what is it? It's centrifugal force, because he's doing the circular motion. Now we have a centrifugal force, which must be equal to the Coulomb force. And by summarizing this, you get this relation. Okay. And then following the second assumption, in which we assume that the angular momentum, which is the radius of the orbit multiplied by the linear momentum, must be equal to n times this Planck constant divided by 2 pi. And then you can combine this equation, which has a v here, and then also this equation. And then if you properly combine it, please try yourself. You can get the radius of this orbital motion. And then it looks a little bit complicated, but again, you don't have to memorize this, but simply try to remember that this value is proportional, again, to the square of n. Okay, so it actually, again, gives you idea that inside this hydrogen, this orbit of electron must again be quantized. And when this number n is just 1, then this you will have the R equal to A, and this is what we call the Bohr radius. Bohr radius is the smallest radius available for electron to orbit around the proton. Okay, we are not done yet. So finally, what we have to do is we have to calculate the total energy. Okay, so what is the total energy in this case? Of course, the total energy must be the kinetic energy plus the potential energy. And kinetic energy for the electron is, of course, electron has a mass and velocity, therefore it has to be half of mass multiplied by the velocity square. And potential energy is, what is this? This is simply the Coulomb energy, which is the energy between the electron and the proton. Okay, and then we already got the V square from the previous slides. So if you insert it, you can get this. So if you summarize it, now this is the total energy. This total energy here is actually half of the potential energy here. This is exactly the same as what we have learned from the classical orbital motion. Anyway, this is what we have. And finally, you can also write it in terms of n, and then it comes out like this. Try to do this by yourself using the formula given in the previous slide. So finally, the important thing is that this total energy of the electron in the hydrogen is actually proportional to minus of 1 over square root of n. Okay, so again, it gives you an idea that these electron energy levels will be quantized. And finally, again, following the same idea that we have seen before, when electron changes from one state to another, that energy must be supplied by the photon, which has an energy which is Planck constant multiplied by the frequency. And frequency is, of course, the speed of the light divided by the wavelength. So therefore, if you use that relation, now you see that the inverse of the wavelength is simply the energy difference of the electron levels divided by the Planck constant and the speed of light. So therefore, this difference in energy is equal to the energy of the higher level minus energy of the lower level. And by inserting all the values given above, now you finally get the formula, which is exactly the same as the Balmer has originally come up with. Okay, so therefore, Bohr finally successfully explained how electrons exist inside a proton, inside the hydrogen atom. Okay. Okay, just like what we have just seen, Niels Bohr, who is shown here, successfully explained how the hydrogen atom looks like, especially the relation between the energy levels inside this hydrogen atom. And we call his model, his theoretical model, to be a Bohr model. But even though this Bohr model is still considered very important, and it gave us an idea about how to solve the mystery of the atomic structure, it actually was not completely successful. It could not explain the fundamental reason why electron levels become quantized. That is simply what he assumed. So it was not enough. And then it was very successful in explaining the hydrogen atom, but it was only partially successful in explaining other atoms which have higher atomic number compared to the hydrogen. And then the reason was because, well, there were actually many reasons, but some of the important reasons is that the electrons actually do not orbit around the nucleus like the Earth is orbiting around the sun. And electrons are actually matter waves. The Bohr didn't really consider that. So therefore, in order to get the real solution, we actually need to solve the Schrödinger's equation. Okay, that's what we are going to see in the next slide. Okay, so and now finally, let's try to see what is the solution in the Schrödinger equation when you have this atomic potential. You know, in the case of atomic potential, the potential energy that you have to insert into the Schrödinger equation will look like this. This is simply just a Coulomb potential. And if you draw the graph, it will look like this. as you can see, the potential is actually curved. So therefore, it is actually very difficult to solve. And at the same time, you see, if you are moving around the proton, then actually there is actually no x, y, z direction. So even though you are in a three-dimensional space. So therefore, mathematically, it is very difficult. So let me tell you that we are not going to try to solve the equation. And we will just look at the result and then think about the meanings. Okay? That's what we are going to do. So let's assume that now you insert this into Schrödinger equation, and then you need to use the spherical polar coordinate instead of the Cartesian coordinate. But nevertheless, please remember what happened in the case of infinite potential in 3 dimensions. I already said that if you are in a 3-dimensional space, there must be 3 different quantum numbers, right? Just like that, in this case, we again need 3 different quantum numbers. And it looks a lot more complicated because now we have a spherical polar coordinate. And the first one is called the principal quantum number, and just like what we have seen so far. And then the other 2 quantum numbers are called the orbital quantum number and also orbital magnetic quantum number. So they represent how electrons are moving around in a circular fashion. But again, please do not try to memorize the names. The names are not important to you. Just try to understand you need 3 different quantum numbers in 3-dimensional space. And then assume, again, you have this potential energy in the Schrödinger equation. And what eventually you have to do is you have to solve it properly. And then once you get the wave, once you have gotten the wave function, then finally what you have to do is you have to take the absolute square of it, which is the probability density function. And then if you integrate it over the entire area, you will get just 1. It's the normalization condition. So if you follow the correct procedure, then you will get the right solution. And then let's try to see what it looks like in the next slide. Okay, now this is how the ground state, which means that the energy becoming the low state, look like. And mathematically, is just like this. So it looks a little bit difficult, but anyway, important thing is that it is exponential of minus r, which means that if you go far away from the center, wave function will become very small. And if you are at 0 distance, which is at the center, you will have certain number. And then this is a 3-dimensional object. So basically, it will look something like this. So it is actually not a single 1-dimensional function, but it is a cloud. So that is exactly why we call it electron cloud. As you can see, electron is not orbiting like the Earth is orbiting around the sun. Okay, now you see why we have a different picture. But nevertheless, if you take the radial probability, which means that if you try to count the number of electrons as a function of distance, as you can see, at 0 distance, there will be 0 number of electrons, and it looks like this. So even though this is not a discrete picture, you see that the highest probability of electron to be at certain distance is the largest at exactly the Bohr radius. So that is why, even though Bohr made wrong assumptions, his result was pretty much, it actually gave us a good idea about what is actually going on. And this, the correspondence between this Bohr radius and then the actual wave function is the reason why Bohr model was partially successful. Okay, and then if you go to n equals 2, now you are at higher energy state. So therefore, it will be the first excited state. And now wave function will change it like this. So in that case, it's still spherically symmetric like a sphere. But as you can see, there is an area where there's no electrons. And that is why, the reason for it is because it forms a wave like this. So if you have a sine function like this, there's a certain area where the density becomes 0. So it actually gives you an idea. Now you start to see the shape, of the matter wave. Okay, and actually this is the case when you have no orbital angular momentum, but with the same n, if you introduce orbital angular momentum, now the wave function start to look different. It looks asymmetric, not spherically symmetric. So in that case, again, the reason why we have this kind of shape is because now going around this direction, it's just like try to imagine it's going up and become 0 and go down. So therefore, along that direction, it forms another wave-like pattern. That is why we have this kind of strange shape of the so-called electron cloud. Okay, so of course we can express this exactly using mathematics, but trying to solve will be too difficult for you. So therefore, don't try to memorize all the results, but just try to remember in real atoms, electrons are not orbiting like the Earth is orbiting around the sun, but this probability density of this matter wave form something we call the electron cloud. Okay, and the reason why they form electron cloud is because they have a wave-like pattern. Okay, and finally, if you go to a very high number of n, the electron cloud will look like this, and because they are confined in a narrow range, now it again start to look like classical orbit. Now again, you see the correspondence principle is working here. Okay, so that is the end of this semester's online lecture. So let's make a summary finally. In this lecture, we have learned the electron wave function in the case of infinite potential well, and also in the case of finite potential well. And from this finite potential well, we have seen a very important quantum phenomena, which is quantum tunneling. Okay, and then finally, not finally, we also discussed what is the ground state, meaning the lowest energy state or the quantum number being 1. And also we learned that there are excited states which has the quantum number larger than 1. So n equal 2 was the first excited state, and n equal 3 was the second excited state, and so on. Okay, so which means that the energy levels in quantum physics or quantum system are quantized. And finally, we learned the Bohr model of hydrogen atom. And also, we have seen what the exact solutions of Schrödinger's equation in hydrogen atom look like. Okay, so here we have learned very new concepts. Maybe some of them could be very difficult to you. But here, well, there are many things you don't have to memorize. Just try to get the idea instead of trying to memorize difficult equations, okay? Okay, so this is the end of this week's online lecture. I hope you liked it. So again, I will see you next week in the classroom, and I will take questions and try to solve some exercise problems, okay? And then thank you very much for your patience and watching all these online lectures. And I wish you a good luck on the final exam. Okay, thank you.